Linear operators are mappings. Let us say we have a map F which takes the vectors of a vector space V1 to another vector space V2. Now this map F, or this function F which maps the vector of V1 to V2, this will be called a linear operator, or it can be represented by a linear operator if it satisfies the following condition: F of A V1 plus AV plus BU, where V and U, they both belong to the vector space V1, and A and B are the scalars on which the vector space V1 is defined, then F of AV plus BU should be equal to A F of V plus B F of U, and F of V, this goes without saying, F of V and F of U, they belong to V2, because this is what the transformation is. The F maps the vector of V1 to V2, but if we have a combination of vectors in V1 on which F is acting, then it should satisfy in this fashion. Then we can call it a linear operator. Why we are interested in linear operator? Because linear operator are a very important tool for quantum mechanics, which we will learn in this entire course. So one interesting fact about linear operator is any linear operator can be represented in a matrix form. So if we are given a linear operator A, which is again like acting from on vector space V1 and results in vector space V2, then we can write the matrix form of A if we know the action of A on the vectors of V1 and yielding V2. So for that, it will be like A acting on vector V gives us W, let us say, where V is from V1 and W is from V2. So this is given to us. Now this is for every vector V given in V1. We know the action of A, the operator A on V, and we know what W we get. Now let us say that we choose an orthonormal basis. Let me remind you what was orthonormal basis. It's the a set of vectors ui such that the inner product of ui with uj gives us delta ij. So let us uncompress this statement. If I is equal to j, then this is the norm of the vector u, and then it should be equal to 1. If I is not equal to j, then they should be orthogonal, so the result should be 0. And this is the maximum set, maximum possible set in a given vector space. And we are taking O and B in V1 vector space. Now, if we apply A, if we know the action of A on all the vectors of all the vectors of V1, then we know the action of A on UI also. And let us say we get WI output. Okay, so if you remember what are the properties of orthonormal bases, that they are complete and they are so it means we can write any vector in as a linear superposition of UIs. So in other words, any vector V can be written as sum over I alpha I ui for all V, and we of course find different alpha coefficients. Alpha i's are given as the inner product of ui with V. So this implies that we can write V as sum over I ui V ui. We can reshuffle since this is a scalar and this is a vector. They commute in a manner of speaking. So ui and V. Now we have product of 3 vectors. Okay, in some or the other way, this is the scalar product, this is the operator product, this is the outer product it's called, and this is called the inner product. We can redistribute it ui since summation is over I, we can take all this, and this is V. Now you see, this is an operator, and we have decomposed, we have rewritten this equation as an operator acting on vector V, the original vector V. So this is true for all the vectors V. So this implies that sum of I, Ui, Ui must be equal to identity. Okay, this is called completeness. So if this is the case, then you can write every vector V as a sum of the orthonormal basis Ui, then this outer product of Ui and sum over I should yield an identity operator. Okay, identity operator is something which acts on a vector, gives you the same vector. Now, why we have gone so far into this mathematics? Because our original task was A acting on Ui is giving us Wi. It means if we take the product of, if we multiply the whole equation from the right side by this quantity, which is the bra of Ui, so that we can Ui equals Wi Ui. This is what we get. Now we can take sum over I, and we can write it as A acting on sum over I, Ui equals sum over I, Wi Ui. This I'm just writing short form as this, I'm writing as this big cross. Don't get confused here. But now we use the completeness relation that Ui was orthonormal basis, so this must be identity. So A times identity is A, and we are getting sum over I, omega I, Ui. So this is one expression for the operator A, which is acting on the vectors of V1 and yielding the vectors of V2. Now you can just simply see A acting on V will be sum over I, omega I, Ui, V. And this is a scalar. Let us call it alpha I. It becomes sum over I, alpha I, omega I. So this is all good, but where are the matrices here? Okay, so to find the matrices, what we do is, let us take a simple case. Let us say A is acting on V and giving the vectors of V. It means V1 and V2 both are the same linear operator, vector spaces. Okay, it will work for anything, but let us take the simpler case. Then and let us say the ONB, orthonormal basis Ui, is written in the following way. The ith vector is all the is a column matrix, one-dimensional column matrix. All of the elements are 0 except 1 on the ith position. Okay, so this is our U. Okay, we can have we can choose more complicated U also, but if simple works, why not work with the simple one? Then, and so since V is going to V, then our Wi can also be written as, let us say, beta ji uj. Since and every vector can be decomposed as a linear superposition of the orthonormal basis Ui, so every omega Wi also can be written as a superposition of Uis or Ujs. So now, since A is sum over I, omega I, Ui, this can be written as sum over I, sum over j, beta ji, uj, ui. Now, what is uj, ui? It is vector which is 0, 0, 0, 1, 0, 0 somewhere. This is the jth position. and it's the Hermitian conjugate here, that is 0, 0, 1. This is the ith position. So this will give us a matrix which is 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And this 1 is at j ith position. So this uj ui is a matrix with having just 1 1 and all other zeros, and that 1 is at the ji location. So if we put everything together, then we get A to be beta ji and everything else is 0, and sum over j and I location wise. So this is a strange kind of sum. It's not a normal sum because it's operators also are changing location. So it will become beta 1 1, beta 1 2, beta 1 3, and so on, beta 2 1, beta 3 1, beta 2 2, beta 2 3, and so on. So this is the matrix representation we were aspiring for. So now let us recapitulate what we did. We are given a linear operator A which acts on a vector space V1 and results in V2. Now we want to find a matrix representation of A. To find the matrix representation, first we realize that if we apply the matrix A or operator A on an orthonormal basis ui, we get a vector or a corresponding vector omega I. And by using the completeness relation of the orthonormal basis, we can find that A is indeed the sum over I omega I outer product ui. Okay, so this is still abstract because we do not have any representation of the vectors ui or omega I. So to get a proper matrix representation, first we represent the orthonormal basis ui as a column vector. So that bra becomes the row vector, and we decompose omega I in similar orthonormal basis. For simplicity we assume v1 equals v2, but if it is not equal, then omega I can be decomposed in some other basis of the vector space v2. So once we decompose omega I in the same orthonormal basis uj with coefficient beta gi, then we substitute this expression and this representation, matrix representation of the vectors, and we get a corresponding representation for the operator. So this establishes this confirms our claim that every linear operator can be written as a matrix, can be represented as a matrix. So this fact will be very useful, and since we are working, this course is on foundations of quantum mechanics, we will be dealing with only matrices most of the time, and very few times we will be using abstract operators. So some interesting facts, some interesting things about operators, linear operators. If you have two operators A and B such that we say A equals B, what is the definition of A? Equality. So when we say A is equal to B, then it means A acting on V should be equal to B acting in the same vector V for all the vectors V in the vector space V1. V. Okay, so this is the only definition to say A equals B, that it should be the action of A and B on the same vector should be same for all the possible vectors. Okay, so this is what we call the equality of two operators. If you have a vector psi and another vector phi, we then outer product psi, outer product phi, which I write psi big cross phi, this is also a linear operator. Okay, now if we have a vector psi and a phi, and we apply a linear operator A on phi, which will give us phi prime, then the inner product of psi and phi prime is psi phi prime, which is psi a phi. And this is basically a product of three matrices, 1, 2, and 3. And it doesn't matter in what order we multiply, as long as we keep this order. So whether we multiply it this way or we multiply it this way, it does not matter. So we can also write it as psi prime and phi, where psi prime is something acting on psi. This is not equal to a psi, but we write this something as a, this symbol which we call dagger or Hermitian conjugate or adjoint psi. So this a dagger is called the adjoint operator. In quantum mechanics, we are more familiar with Hermitian conjugate. So a dagger is Hermitian conjugate of a. Since we are, I'm a physicist and we are doing the physics course, I can take the liberty of saying that phi and cat phi and bra phi are also Hermitian conjugate of each other. So I can write phi dagger equals psi. Operationally, this is correct, but probably some mathematicians will take it as an offense. But for us, this will be the same thing. So when we say an outer product, it is actually psi and phi dagger outer product, which is a product which is psi phi. Another thing to understand in about linear operators is the trace. How do we define a trace of an operator? We generally know that if we are given a matrix, we just take the sum of the diagonal elements. The sum of the diagonal elements of operator A, matrix A, is the trace. But more generally, trace of A is defined as sum over I ui A ui, where ui is the set of orthonormal bases, complete and orthonormal bases on a vector space. This is how we will define the trace of a matrix. Now there is a class of there are a few very interesting type of linear operators which we will be using throughout this course, and that is important class of operators. So in this class, we have first is the Hermitian operators. They have another name which is called self-adjoint. So as it is evident from the name self-adjoint, it means a given operator A, if it is equal to its adjoint, then it's self-adjoint and it's Hermitian operator. So what is so special about this? Before going to that, let us discuss. So if you have operator A acting on a vector phi, and you get the same vector phi with a scalar multiple lambda, then these vectors are called characteristic vector. We are more familiar with their other name, which is the eigenvector, and the scalar lambda is called eigenvalue. If you have phi n equals lambda n phi n, then the set, there are many eigenvectors and eigenvalues. Then for a Hermitian operator, lambda n eigenvalues are always real. Not just that, phi n, the set of all the eigenvectors of A, they form an orthonormal basis and complete, orthonormal and complete basis. So let me say it again. For an Hermitian operator, for a self-adjoint operator A, the eigenvalues are always real and eigenvectors form a complete and orthonormal basis. Now, proof of that is fairly straightforward. Let us say we have A acting on phi n gives us lambda n phi n. Let us take the inner product of this with some phi m, lambda n phi m phi n. Okay, so like I said, we can take the product like this or we can take the product like this. So if we write this as inner product of A dagger acting on phi m and A dagger is equal to A, so A acting on phi m phi n, then the right hand side is lambda m phi n, and right hand side is lambda n phi m phi n. Or we can say lambda m minus lambda n phi m phi n is 0. Okay, so now let us say case 1 when m equals n. Okay, sorry, this should be lambda star. So it's a conjugate, right? So it's lambda star. Yes. So when m equals n, then lambda m star or lambda star equals lambda m. This is lambda m star equals lambda m. This implies that all the lambda m's are real. Okay. So it means all the eigenvalues are real. The first thing is proven. So case 2, when m is not equal to n, so we can rewrite this equation as lambda m minus lambda n. Since all of them are real, we don't need to keep the complex conjugate. Phi m phi n equal to 0. So this is a number scalar, this is a scalar, and the product of the two scalars is 0 if and only if one of them is, at least one of them is 0. Since m is not equal to n, and let's assume that this is a non-degenerate case, it means all the eigenvalues are different, then this quantity is not 0. So it must be that phi m phi n should be 0, which implies that phi m is orthogonal to phi n whenever m is not equal to n. And this proves our whole conjecture, our whole claim that the eigenvalues are always real for a Hermitian operator and eigenvectors are always complex, orthonormal and complete. You just see that where have we used the property that it has to be a Hermitian operator. The property we have used that it has to be a Hermitian operator is here, that A acting on phi and A dagger acting on phi is same. It means A dagger equal to A, that is the definition of equality, phi n, let us say. So this is where we have used and we could arrive at this equation. Of course, we are not assuming from the beginning that the eigenvalues are real. So we have taken complex conjugate, and this ultimately we proved the whole claim. Another class of interesting operators is the anti-Hermitian. Or skew symmetric, skew Hermitian, skew Hermitian operator. So as the name suggests, A, if it is an anti-Hermitian operator, then it should be equal to minus of A dagger. So it's not equal to its adjoint, but it's negative of its adjoint. Now very easily we can see that if we have a Hermitian operator H and we multiply it with the I, which is the square root of -1, the dagger of 8 is always minus I H dagger, which is minus I H. So this implies that I H is always anti-Hermitian. We can claim here that all the anti-Hermitian operators can be written as I times Hermitian operators. And this is what we will be using throughout this coursework. Next class of operators. So if A is IH, then we can use all the properties of the Hermitian operators to redefine the properties of the anti-Hermitian. For example, if the eigenvalues of H are lambda i's, which are real, then eigenvalues of A will be I times lambda, let me call n, there are too many i's, so it's purely imaginary. So in that way, we can define many other properties. The eigenvectors will remain the same. So eigenvectors of anti-Hermitian operator are always orthonormal and complete. And whatever property we have for Hermitian operator, we can see how it translates to anti-Hermitian operator. Next class of operators which are of interest to us are the unitary operators. Operator U, which is unitary, is defined as U is an operator which is the adjoint of U is actually the U inverse. Okay, the operator U is unitary operator U is defined in such a way that the adjoint of the unit the operator is its inverse, or in other way, which is more familiar way of writing, U times U dagger equals U dagger times U equals identity. Let me restate it, that U times U dagger equals U dagger times U equals identity. If only one of the conditions are satisfied, not both, then it's not a unit. It need not be a unitary operator. Okay. For a unitary operator, both the conditions must be satisfied, that U dagger U and U dagger should be identity.